Hi, this is Margaret. Let's get more familiar with the words that we use when we talk about electricity. Now, you might like to use the flow of water as an analogy to help you think about what these words mean. And I've drawn a crude diagram of a water system here. I've got water coming into a storage tank, and you know the deeper the water is, the more pressure there is, and the pressure will force the water to flow through this pipe, and then it will turn this water wheel. Whoops. And just because electric circuits need a return path, I've drawn in a return path for the water. You might not usually see that in a water wheel. So the basic idea is that voltage is analogous to, it is kind of like the pressure that pushes the water through the pipe. And current is analogous to the flow of the water through the pipe. So voltage, you could think of it as being like electrical pressure. It's more precisely, it's potential energy. It's the difference in potential energy between 2 points that makes current flow. But I like to think of it as pressure. And we measure voltage in, surprise, surprise, volts. You will run into some other words that people use. One word that people use is potential. And that's because we're talking about potential energy. That's what makes voltage, and that's what makes current flow. Another word you will run into is EMF. This is an old-fashioned word from maybe 1 or 2 centuries ago. It stands for electromotive force, and people used that term back when they didn't really understand much about electricity. We now know it's not a force, so it's not an electromotive force, but you will still see this, and a lot of electricians' handbooks will use E for voltage. But we're going to use V for voltage, and we're going to measure it in volts. It's interesting to think about how all over the world, all kinds of mechanisms operate through a difference in some kind of potential energy. So just a rock rolling down a hill, there's a difference in potential energy from the top of the hill to the bottom. Water flowing through a pipe flows because there's more pressure on one end and less pressure on the other end. So for example, you open your faucet and the higher pressure on the other end of the line makes water come out. Or in a dam, pressure of the water behind the dam makes the water flow through this tube. Likewise, in a wire, it's a difference in voltage that makes current flow through the wire. And current is flow. Current is a rate of flow. Specifically, it's the rate at which charges flow through the wire, but that's caused by electrons flowing through the wire. Never mind all that. Current is flow. And we measure current in amperes, but most of us call them amps for short. And you will see some people call current, they'll refer to that as amperage, and it's measured in amps. Just an interesting side note, you know, it looks like electricity flows really, really fast. So you turn on a light switch at the edge of your room, and the light on the other side of the room comes on almost immediately. And that shows you that current is traveling really fast, almost the speed of light. What's interesting is that the electrons themselves don't move that fast. Electrons move about, one electron will move about 2 or 3 inches per minute. And an analogy of what's happening you could think of is, what if you had a tube with ping pong balls in it, tubes filled with balls, and you push one bulb into the tube, and immediately a ball pops out the other end. And if you didn't know better, you'd think, oh, that's the same ball going really fast, but it's not. One is pushing the next one, pushing the next one, and so forth. Just an interesting side note. Resistance is pushing back against current flow. It's an opposition to flow, and we measure resistance in ohms. If you have an electric stove with a burner that gets hot, you are using resistance intentionally. On the other hand, if you have wires in your wall that are too small and they get hot, you are using resistance when you don't mean to. And in fact, that's really probably the fundamental purpose of the National Electrical Code, which we'll see from time to time this term. The code is all about preventing fire as well as electrical safety. And they do that by figuring out how big do the wires have to be to keep them from heating. Okay, then power, which we measure in watts, and we can also measure it in horsepower. There we can directly translate. But when we talk about electricity, we'll use watts. Now, work is the transfer of energy through a distance, and power is work over a period of time. So, for example, let's say we're building a brick wall, and we each have a pallet of 100 bricks that we have to move from the truck to the job site. So I'm feeling kind of wimpy that day, and I'm just going to carry one brick at a time. I'll get them moved, but it'll take me a while. You're feeling pretty strong that day. You're going to carry 10 bricks at a time. So by the time we get done moving our pallets, we'll each have moved 100 bricks. So you and I will each have done the same amount of work. However, you will have done it much faster. You will have used more power because you have been able to move 10 times as many bricks at a time. This picture of the horse is related to the idea of horsepower. And the idea is, if this horse lifts 550 pounds 1 foot, that's some work. If the horse can lift it that far in 1 second, that amount of power is 1 horsepower. So it's how much energy it takes to lift that much weight that high in that much time. And if you want to translate from horsepower to watts, or the other way, 1 horsepower is exactly the same as 746 watts. Power is a rate. Watts is a rate. It's not a quantity. So when we say a power plant is so many kilowatts, we can't say the power plant produces this many kilowatts per day. That would be nonsense. It is producing power at a rate. It's just like when you talk about water going through a pipe, you talk about how many gallons per minute is the flow rate. It's like that with power. So watts is a rate. If you want to measure how much power you used in a particular time, which you do on your power meter on the side of your apartment or your house, you could go, how many watts did you use per hour, or how many thousand watts did you use per hour? That's a kilowatt hour. That's a quantity. But watts is not a quantity. Watts is a rate. If you live in a small house with, let's say, no air conditioning, just your basic small house, you probably use power at the rate of 1,000 watts, or 1 kilowatt. If you turn a crank on a hand crank generator like this one pictured, you could probably generate power at a rate of 100 watts, and so you could light up a 100-watt light bulb. So there you are, volts, amps, watts.